Okay, guys, so in this video now we're gonna do 10.6, and as you guys see, I skipped some of the parts of the chapter, and the reason because I cover those concepts, that overlap with the other parts of the chapter. And so what I try to do is when I teach guys, I try to connect the concepts that are related so that you can better see the, better see or have a picture of the better, I guess, clearer understanding of the concepts in here. And that's why I sometimes go from one part of the chapter to the other, so that to connect several things, so that you can have a better understanding of the concepts. All right. So now I'm going to do 10.6 classes of chemical reactions. I'm going to abbreviate reactions as RXN. All right, so let's start with the first type of reaction. It's called synthesis, or also it's called combination reaction. Combination reaction. Combination. So synthesis combination. Now, how do you know that you have a synthesis reaction? I have my own definitions. In other words, simple terms I use to identify different classes of chemical reactions. And the synthesis or combination reactions, you go from simple to complex. In other words, you have simple substances, usually they are elements, and then they are forming more complex substances, they are compounds. All right, just guys, bear in mind. So a typical reaction, combination synthesis reaction will be some reactant X, some element X reacting with element Y, producing a compound XY. And one of the examples, guys, of this synthesis combination reaction was when you did H2 in the previous videos plus oxygen gas producing H2O liquid. And again, this is not balanced, but this is now balanced. And now look, we got simple elements, hydrogen, oxygen, and now we form more complex substance, which is in this case now H2O water compound here, okay? And there could be other reactants. Could be, you can have H2 gas reacting with the chlorine gas, Cl2 gas, producing 2 HCl and HCl gas. Now, again, this is a combination reaction synthesis because you go from simple to complex. All right. So what's the next type of chemical reaction? So if you go, guys, from complex to simple, or reverse of synthesis or combination reaction, this type of reaction is called decomposition reaction. Decomposition reaction. Okay, what are the examples of the decomposition reaction? Well, first of all, let me just show you this. X and Y will decompose into the compound into the elements in this case. All right. So what are the examples of this reaction? We can now take these reactions here and just reverse them. And if we had, for example, 2H2O liquid, we use electric current. We can use electric current and decompose now the H2O molecule into the 2H2 gas plus O2 gas. Or you can have now reverse this formation of hydrogen chloride gas. Now you got 2 HCl gas decomposes into now simple substances such as H2 gas plus Cl2 gas. There could be, of course, other different examples of the synthesis decomposition reactions. One of which comes into my mind, for example, you got KClO3 solid, and then you decompose it with temperature and it becomes KCl solid. Let me just correct that. Supposed to be solid here. KCl solid plus O2 gas. This will also be, guys, an example of decomposition reaction because you went from complex to simple, even though this is not an element here. It's still a compound, but it's still, I mean, this compound is simpler here than the reactants. All right, so it's a decomposition reaction. It went from complex to simple. And of course, this is not balanced, but if we put a 2 in here, and we will, let me see, put now 3 in here, and we're gonna put 2 in here. Now everything here is balanced, okay? Now, so these are, you know, now I just provided you guys examples of 2 different types of reactions, synthesis, decomposition. Now I'm gonna give you guys some more different types of reactions. And the next one that comes into my mind now is what's called single replacement reaction. Now replacement, let me just make it replacement reaction or reactions. Again, I just abbreviate RXNS by just the word reactions. And so what is the example? What's the model here? How do we approach now or recognize a single replacement reaction? So you got like some element, let's say, by itself, and then you got a compound. Usually it's a compound here. And so what happens is this element will kick out this, one of the elements in the compound will kick it out, and now will take its place. And the element that it got kicked out becomes a single. Okay, so now you got X and Z forming new elements, plus now Y got kicked out. And this is an example, guys, of a single displacement reaction. Now, what are the examples of a single displacement reaction? One comes to my mind. Actually, I look at the textbook now, I can see a very good example. Let's say I got zinc solid, and it reacts now with, let's say, H2SO4. And so what's going to happen here, a single, remember, single displacement, single elements will now come in and kicked the hydrogen out, and it will take its place. It will be zinc now, SO4 plus H2. And remember, guys, you always want to put now the states of each chemicals, the physical states, right? Aqueous, and this is gas, of course. Okay, so again, what happened here is what's called single replacement reaction, and single element attack now this couple that contains H plus and SO4 2 minus, and then it kicked out the hydrogen, took its place right here now with the sulfate, and the hydrogen now became a single. So single comes in, breaks up the couple, you can think that way, and new couple now formed, and now a single element is produced now, okay, which is different from the single element that went into reaction. What is another example? Well, again, I'm looking in your textbook right now, and there is another one here. Let's say nickel. Nickel by itself reacts with, let me see. Yeah, reacts with, let's say, HCl. And always, guys, remember, when you have this single replacement reaction, you generally react a certain element that if it kicks out the other one, this one has a positive charge in here, positive oxidation number here. So when it kicks out, usually positive, of course, replaces the positive, because if zinc did not form 2+ ion by losing electrons now to hydrogen here, it would never be able to bind or to actually be attracted to SO4 2 minus. There would be no attraction, because if they were both negatively charged, they will repel, and never, guys, you would see them, you know, close to each other. But so just bear in mind that if a single element kicks the other one, they actually have the same charge. Now, look at the nickel now. Nickel is also, in this particular case, It has the oxidation number of 2+, eventually it'll form, but it's going to be positively charged eventually. Right now it's 0 charge here. And so when it reacts, it would form NiCl2 aqueous here. And what's get kicked out here again comes in. This one gets kicked out as hydrogen gas. And all you have to do now, balance the chemical reaction, just putting the 2 in front. Now, these are generally, when you have a single displacement to single replacement reactions, are oxidation reduction reactions. And usually when you look them up, there is somewhere in your textbook, there is what's called activity series, metal activity series. And you would actually, if you don't know the products of these reactions, you can look them up in the metal activity series. And they will tell you guys what the products are based on the metal activity series. Now, one more reaction, guys, well, actually a couple of more I want to mention here is what's called a double replacement reaction, sometimes also called double displacement reaction. All right, let me just write it down. Double replacement reactions. They usually, guys, precipitation reactions. And you probably already done some lab experiments where you had to react a certain salt with another one, and then then you form a solid as a product, and the solid formation of a solid is pretty much told you that the reaction will occur because you will see a precipitate right in the bottom of the let's say test tube. Now, what's the model now? How do you know this is double displacement? Let's say you have one couple AX, and then you're reacting with another couple, let's say BY. So now this one here and this one here, the cation here, will kick out the B and take place now with the Y, and the B will now come in here and actually take the place of where used to be the A. So in other words, you're going to have now the following products here. You're going to have a BX plus AY. So you see how this and this, all they did, they just exchanged the places here. They just exchanged the places, and that's exactly the way with the arrows, guys, I showed you. Now, what could be examples, guys, of this reaction? I think in the lab, you guys already have seen these reactions. You got HNO3 silver nitrate solution aqueous reacting with sodium chloride aqueous solution. And look what happens here now. This will come and kick this one out, and this will take the place of silver here. And so now we got here AgCl, and it will be solid according to the solubility rules, guys. Check out the solubility rules. Again, double displacement reactions, generally they are precipitation reactions. And so now the new one will be now here plus now, and then the sodium will take the place of what used to be the silver, will be NaNO3 aqueous. And because you form a solid in here, that's what drove the reaction to completion to make now this product. Now, again, all I did, I just followed this model, double replacement or double displacement reaction. They will just exchange these cations here, positively charged ions. They will just exchange the partners here, the positions here. And again, why am I calling them cations? Because the Ag has a positive 1 charge in here, and the sodium has positive also 1 charge in here. Chloride, negative 1 charge, and the nitrate, this whole thing has a negative 1 charge. Okay, so again, double replacement reactions, all you're doing is just exchanging the cations here. Now, let's take a look at another reaction, and let me think of some. Well, let's say let me see. We can do another silver nitrate. I'm looking at your textbook, but let me just maybe go to some example here in the bottom. I'm gonna try some of the some of these reactions here. I see here this one here is NH4Cl aqueous plus AgNO3 aqueous again. And so again, this is a double displacement reaction here. This ammonium NH4 plus ion kicked out this Ag plus also ion, which is cation also, and this took its place. And the reason, again, this reaction went to completion and actually produced the products is because AgCl, again, form a solid here, according to the solubility rules. And then the other product, you got NH4, NO3, because NH4 is +1, NO3 -1. So you have this 1-to-1 ratio to make this whole thing, this whole molecule here neutral. And that would be your second example, guys, of double replacement reaction. And so I'm not going to do example 10.5 because I think I went into great details for you guys to be able to do this example. I gave you guys some examples of other chemical reactions to be able to identify which one is the synthesis or combination reaction, which one is a decomposition, which one is a single replacement, which one is a double replacement reaction. One more, guys, type of reaction I want to mention, which is a very important one. It's called a combustion reaction. Combustion reaction, or reactions, plural here. And so the combustion reactions are pretty much what you need in this reaction. You need some kind of oxidizer. Usually, guys, they use oxygen is one of the reactants. And then the products, so this is the reactant here. And then the products here, to watch for, guys, heat evolving and light. You're going to see one of the products will be both actually accompanied by both heat and light. Now, what are the examples now of the combustion reactions? Well, a typical one, you guys have your methane on the stove that you using during the cooking, right? So plus now O2, there is your oxidizer here, O2 gas. And what you're producing here is a CO2 gas and H2O liquid. And so this will be combustion reaction. Guys, I mean, just check it out. Just go to your, if you have a gas stove, you turn on, do you see the light? Yes, you do, because you're cooking it, right? And you see the light, right? You see that burning gas. And you also feel the heat. That's how you cook, right? Because the energy in the form of heat is being transferred to cook your food. So that is your example, guys, of a combustion reaction. The only problem here is that this is not a balanced chemical reaction. So this is 4. Let's make it 4. And now you got a 2 in here. All right, what's another example of combustion reaction? Well, actually, believe it or not, guys, the combustion reaction also could be this H2 gas plus O2 gas, even though we talked about it's a combination reaction. But the reaction, could be classified, in other words, it could be 2 classifications for the same reaction here. And the reason is because when you bring these 2 together, and again, I'm going to post the video, if you guys remind me of this reaction when I pumped the balloon with the hydrogen gas. And the next thing I did, I brought a little flame, and you see the explosion there. Not only explosion, you see the light, and also, of course, there's a heat released. And so once you got a light and heat as part of the products, that is your combustion reaction also. So formation of water here will be also a combustion reaction. But usually, guys, in the exam, if I ask you this question, I go with something organic, something like this. Or I can give you another example. Let's say I got C3 H8 plus O2 gas. This is, of course, propane gas. Like you guys have a propane tank for cooking. This is the gas inside. And then you form CO2 gas plus H2O. And remember, guys, if you have a propane, and remember how you cook using your stove outside, right? Your grill outside. So again, do you see the light part of the products? Yes. Do you feel the heat? Sure. You're cooking your food right there. And so again, this is not a balanced chemical reaction. This 3 here, 3, I have to make it now. 8 hydrogens now, there will be 8. 6 oxygens plus 4 will be 10 oxygens. So this is now a balanced chemical reaction. I'll put the 5 in here. And this is an example again of combustion reaction. Not only that, you're gonna have now your CO2 H2O. When you burn organic, guys, during the combustion reaction, that's what you always have to watch out for. When you have a combustion reaction, burned organic, guys, the presence of oxidizer, oxygen, you pretty much always get CO2 and H2O. The only I guess times when you're not going to have a CO2 here as one of the products is when you don't now have enough of oxygen present in at a certain place that you are conducting this combustion reaction. So in that instance, guys, you're gonna form carbon monoxide, and also one of the products could be just carbon soot. You're gonna see the black deposits of carbon. And very important, guys, when you do combustion reactions, hopefully not in your house, and because of the limited amount of this oxygen present indoors, guys, which are going to wind up happening, producing a lot of carbon monoxide, and this is where carbon monoxide poisoning occur, guys. So never do the combustion reaction, guys, such as, let's say, if you're cold in the winter and you decide, you know what, I'm cold, let me just turn on my gas, the oven, gas, in the oven, and also my, turn on the gas, kind of you cooking. Instead of for cooking, guys, turning on for heating. Just be careful, because since you have a limited number of oxygen molecules in your house, you're going to start also producing, guys, carbon monoxide. And that's where carbon monoxide poisoning, guys, may occur. So just be careful with these combustion reactions when you burn organic substances. All right, guys, I'll see you in the next video. I'm going to now in the next video to do the chemical equations and the mole concept.